Hello friends, so from today I am going to start a new lecture series about the design and analysis of the structures member. So like beams design, column design, slab design. So these type of flexure members and compressor members we are going to design in this lecture series with the help of SP16. I think you have heard this type of name. What the use of this? By this you can easily design the beams and columns and slabs and footings. It's based on our Indian standard course. It's based on our Indian standard code, that is IS 456 2000. So anything version, maybe anything, because I have the I think 19 and 90, 19 and 19 I check 1980. Okay, I have the version of 1980. So the IS code will also I think should be previous. So okay, so now we are going to design the beams, columns, slabs and footings. For the static load, I repeat, we are going to design for the static and moving load as well. Static and moving, what's the mean? If you want to design the bridge beams, this is the bridge deck, and here this is the deck and the beams we have already. One second, here is some beams. Those are called what? These are called girders, because if the beams are designed for the moving load, then the beam is called as girders. Okay, and the beams is for simply for the static load. This is our deck, this is our longitudinal beams, longitudinal beams means longitudinal girders, they're the same, and the laterals are also there, which are going inside. Okay, which are going inside throughout the plane. So this is the section view, means front view of the bridge. Here the piers, abutment, piers, this is foundation, same. So here are some beams that should be designed for moving loads. So I am going to first of all discuss about the static loads. So let us, we have the one simply supported beam. This is simply supported beam, and here is one loading like UDL. Okay, this is UDL. UDL of, you can consider it as a 20 kilonewton per meter, and the length of the beam you can consider as 10 meter. So this is our beam that we want to design. Okay, for the 20 kilonewton per meter live load, this is a live load, means excluding the dead load. Dead load means self weight, because there is self weight of the beam also there. So this will create a something moment, some moments, so that will be also considered. So okay, this is our beam, this is simply supported, and UDL is applied here. So what we have to do, we have to just make the bending moment diagram for this. The bending moment diagram for this type of loading case, it will come out this like, and the maximum value will be at the center. So what is the value of maximum? WL square by 8. Okay, what the value? WL square by 8. This is the case. So we have to design the beam, but we don't know the size of the beam. What is the size? So you can take anything for the starting. Set. For starting point of view, you can take the beam size like beam have the size of 350 mm by 500 mm, like this. We are taking this size of beam to design. Now we have to decide the what is the reinforcement, means reinforcement detailing we have to decide. Decide means we have to design the reinforcement, how much reinforcement should be present at the top and at the bottom of neutral axis. So you know the neutral axis also. This is our cross section of this beam, and this is the neutral axis that go from the center line, means centroid. Okay, this is what this is 500 for our case. This is 500 and this is 350 mm. So this is the case that we are going to discuss. So beam have the size of this, and the maximum bending moment we can get from here. So maximum bending moment due to dead load, because here the dead load also of the beam, dead load means self weight. So self weight is what is the self weight? So you can easily calculate the self weight. So what is the value of bending moment? W becomes WD L square by 8. Okay, WB L square by 8, and the WD is what? Self weight, means dead load. So what is the dead load? So you can get by easily, you have to just multiply with the 25 and the size. Size is what? 350, so I put it in meters, and for 1 meter. Okay, this is the density, this is weight density of concrete. This is weight density and this is our volume. So you know, if I will multiply the volume with the weight density, that what will come out? Come out as kilonewton. Okay, but we have to consider the length is equal to 1 meter, so you have to put it per meter. And what is the value of it? You can calculate by the calculator. 25 multiplied by 0.35 multiplied by 0.5. Okay, what is the value? 4.375. This is the dead load. And what is the live load? DL. What is the live load? Live load is already given to us, kilonewton, 20 kilonewton per meter. You have to just add them, dead load plus that will become W total. What is it? 20 plus 4.375, that will come out as 24.375 kilonewton per meter. So this is our W net W. Now we have to factor it also, because as per our code IS 456, you know, IS 456 2000, what is it saying? The limit state matter is saying that we have to multiply the load with the factor of load factor. Factor of load factor, what is the load factor? So load factor, we know that is already 1.5. So you have to just multiply with the WC. So that will become as factor. So factor should be written is as subscript as U. Okay, so you have to just put U at the subscription, add subscripts, and then multiply this value 1.5 multiplied by 24.375. So I again open the calculator and multiply it. Sorry, this is not. We have to 24.375 multiplied by 1.5. 36.56. So I take it as 37. Approximate higher value. So now what is the moment by this? MU. That will become as WU L square by 8. Just solve it. WU means our 37. Length is our what? 10 meter. I think I have given you 10 meter. Yeah, 10 meter. Multiply by 10 means 100 and divisible by 8. Enter. 462.5 kilonewton per kilonewton meter. Once again I forgot the value. 37 multiply by what? 37 multiply by L square means 100 divisible by 8. 462. Okay, 462.5. 462.5 kilonewton meter, that is our moment. That for this moment we have to design moment is what? 462.5 kilonewton meter, that is our design moment. For that we have to design our beam. So now just you have to calculate the mu and go to our code. What is the code? Code is SP16. So in this you can see the flexor member second section, in which you have to just go below and see the tables. So I mark the page also there. Go down, go down, go down. Okay, this is okay. So we have two options, there are two types of beam. First beam is our singly supported beam, and second is our singly reinforced. Oh, it's mistake. It should not be written like this. Singly reinforced and doubly reinforced. So what is the difference between these two beams? This is the type number 1, this is the type number 2. You know the beam section. So if you put the reinforcement only in one side of the neutral axis, that is called as singly reinforced. Okay, and if you put the reinforcement on both the sides of neutral axis, then it is called as doubly reinforced beam. So this is the difference, and why we use the singly reinforced, doubly reinforced. So I will come on this point also. So okay, it should be clear at this level also. So okay, so what is the singly reinforced and doubly reinforced? So first of all you should know what is the reinforced, why we put the reinforcement in the beams, what is the need of reinforcement in the sections. So why we put the reinforcement, I think because you have done your RCC subject, reinforced cement concrete. So for that I think I should give some idea also. So like, one second, what the it's not going like that I want. Okay, no problem, I draw it by one by one. So let us consider this is your beam. Okay, I am so we are saying what? We are saying the we are front we are in front view. This is the support, and there are some other supports also. This thing I have covered in our Stat Pro course also. In that one kind of lecture I have done these things. So this is your beam, and there is something loading, anything, any loading. By this it will become bend. So in which, so this is the neutral axis. Okay, this is the neutral axis because it's going from the center. Okay, this is the neutral axis of the beam. This is like, you can consider it L1, this is L2, this is L3. So this is the purely concrete beam. First of all you should know why we reinforce the beam. Concrete beam, there is not any reinforcement. So what will happen if I didn't put any reinforcement in it? So I just take it down, then I will give some idea. Okay, so this is your beam. So it will become bend. It's bend like this. Let's go down now. I give some This is good. So I drawing only what? Only CG means neutral axis deflection shape, because here the beam also. So beam cross section I something draw like this. This is your beam will bend. So beam will bend along the CG line. Okay. So I should not draw because it will become very complicated to explain. So you know how it will deflect. So this is the deflector shape. So why we have to give the reinforcement in it. So why we give the reinforcement? Because the tension part is also there. A beam will deflect like this, as I drawn here. So beam will deflect like this. So this is your beam. Okay. So this is your beam that I am drawing. So beam will deflect in this way. So this is the cross section. That is so elastic, you can see, but it's not like that practically. So because it's freehand drawing, so it's looking like that. Just uh, listen the things, don't confuse with the diagram. So this is the deflected shape. Okay, this is your CG and this is the whole cross section of our beam. So why we need the reinforcement? Because you know this below means down part, this part going in tension, and this part going in what? This part going in compression. So you all know that concrete material means concrete building material is strong in what? Compression. So it can take compression only. It's weak in what? Tension. It's weak in tension loading. So if the loading will be applied and it will become tension from the bottom, then it will break. It will easily break. It's not take much more load. It's break from here, and the cracks will develop at the bottom surface, and it's go down. It's go up in the direction of neutral axis. Okay. So the cracks will occurs here. Here also become the tension is also there. Here also. So to avoid this, we have to reinforce the concrete sections by what? By the steel bar. So you know steel bar have the ductility, and concrete is what? Brittle material. So brittle materials are weak in tension and strong in compression. So concrete is a brittle material, and steel is what? Steel is ductile material, and the property have the ductile material is that ductile material it's have the tension capacity larger than the compression. So compression I will not take in interest, because the we have to just focus on the tension loading. So tension capacity is more for the what? Steel. So just we have to put this bar in this region. So this is what? This is our steel that I have drawn here. Same. Same in this portion also, because the tensile will develop in this region. And you know, because at the top surface means at the support level, there is tension will develop at the upper region. So here should be the steel also. So at here we should draw the steel. So this is the logic behind the why we put the reinforcement in the concrete sections. Okay. Now, so this is the logic behind what why should we have to study the RCC subject, and what the meaning of reinforced. And reinforcement is what? Any ductile material we can take, but still we should take because the steel has the thermal expansion coefficient. It's a very famous question that will be asked in any interview. Expansion coefficient Same as what? Same as concrete. Because during the thermal expansion, means when the temperature is rising at this location, then they will expand. And if concrete like expand very low, and still like expand, any ductile material is expand very high, so they will lose your bond. So they will lose their bond and the strength will decrease. So that's why we have to take the ductile material as steel and concrete material brittle is already concrete. So that is the reason we have to take the ductile material as concrete. Okay. So now we go to the design part, that we have get this value. So this is the singly reinforced and doubly reinforced. So what is the meaning of singly and doubly? So I have drawn the singly reinforced beam. You know, at this section there is only one sided reinforcement, so this is called as singly reinforced beam. At this section, support section, there is also in one side, means above the neutral axis, so there is one sided reinforcement, so this is also called as singly reinforced. So this all the beam is called as what? Singly reinforced beam. Okay, so this is called as singly reinforced beam. So now we have to design what? Singly reinforced W. So it's your choice what you want. So just I want to design the doubly reinforced, because doubly reinforced beam is more efficient than the singly reinforced, because we have to strip these longitudinal bars also, because we have to apply some stirrups. You know what are the shear stirrups? So these are the stirrups that we have to establish along the length of the beam. So it is more easier to bend, means establish in this region, means doubly reinforced beam, because there is not any bar, so it is not, fixity is very loose, it can't fix at air, it can be moved. So if there is any bar, then it will be more controlled condition. Okay, so in this condition we have to choose as doubly reinforced beam. So I take it what? I want to design the doubly reinforced beam, doubly reinforced beam, which moment carrying capacity, means MOR, moment of resistance, should be more than this value, because the moment of resistance will more this value applied load, applied moment, then our structure, means our member or our beam will safe. Okay, so we have to take the members capacity like that, and we have the section also, we are taking the section what? 350 by 500. So now I am giving you the grade also. So let us take, I have the grade of steel and concrete as M25 concrete. M meaning is what? Mix. Okay, and Fe 415. This is our steel or reinforcement. Okay, so now we have sufficient data to design the doubly reinforced beam. Now we go to the SP16. So you can see the tables and some graph papers here. Here you can see the chart number 2, that is singly reinforced beam, and moment of resistance kilonewton meter per meter width, and Fy it is mentioned also. If your Fy is 250 and FCK is 15 and D is what? So I give you the value of D. What is D? So it is in this table, because you should have all the idea about the SP16. And D minus T dash T 1 second. Okay, this is the all the notations and symbols that you can see. So D is what? Effective depth of a beam or slab. D is what? Effective depth of the beam and slab. So you know what is the effective depth. So I should give some idea for this also, that what is the effective depth. So this is like your beam cross section, and these are the some reinforcement, and this is your overall depth, that is I mentioned as capital D, and this is B. Okay, so what is the effective depth? So effective depth is the depth up to the center of the center, means up to the CG of the longitudinal reinforcement from the top. Okay, like this. So I give you some examples for that. So like this is your beam. No, it's not looking like that. I want, yeah, this type of. Okay, this is your beam and these are the reinforcement. Okay, these are the reinforcement and total depth I have given you same 500 mm and 350 mm. Okay, so what is the effective depth if the dia of the bar is 20 mm? Both have the dia of 20 mm. 5 means dia of 20 mm. So what is the effective depth? So effective depth is what? From the CG to the topmost fiber. This is your effective depth, that is D. And what is this eliminated part? What is this part? So that's named as effective cover. That is effective cover. That is the symbol is D dash. Okay, symbol is what? D dash, and the symbol is D for what? Effective depth, D. So what is, if it is taken as capital D, then D is equal to D plus D dash. Okay, so there is one thing, something more is that from here means from the end portion of the bar to the end fiber. This is called as nominal cover, yeah, clear cover. This is called a nominal cover, a clear cover, that you can see in your code IS 456. There are some tables that depends on exposure condition. According to the exposure condition, there are some values for the clear cover and nominal cover for the beams, column, slab and footing. Okay, so now we can get the D dash by the clear cover also. So what is the D dash? D dash is from air to air, so D dash will become as nominal cover plus this thing. This is what? Half of the dia. Because it's passing through the CG, so D dash is what? Half of the dia, means 5 by 2 plus what we have to add? Nominal or clear cover. Okay, so by this way we can get these things. D dash, everything we can get. So you have to just assume what is the clear cover. So we are taking it as a 30 mm. You can take it as 30 mm, and phi is known. Phi is what? 20 mm. So you can get what? D dash 20 by 2 plus 30, that will become as 40 mm. So you can get the effective depth also, because D is equal to D plus D dash, and capital D is what? 500 mm, that we know. D we have to calculate, and D dash we can get by this 40. So D is what? 460 mm. So this is your effective depth of this beam. That's a very fundamental part for the cross section of the beam, so that you should know how we have to define these all the things for the beam section. So now we go on our last page, and okay, D dash I have covered, because by this way I can cover all the things. So now I go again. So there are some parts. Okay, the chart number 12, that is for singly reinforced. If you want to design the singly reinforced section, then you have to just see these values and can just design. So but I have to design what? Doubly reinforced. So I have to go below doubly reinforced. These are the doubly reinforcement part. So you can see for FI 250 you have to check this part, this chart. But what we have the FI of 4 on 5, that I have given to you in problem. You can see 4 on 5 is our FI. This is called as FI. Okay, yield strength of the steel bar. So we have to give 4 on 5 as FI. So you have to just search the chart. This is FI 250, and if you go below, then you can see singly reinforcement in the table form also there are. So I am taking the singly reinforced knot. This is also singly. This is for slab. Okay, I check it 1 second. This one, okay. No, no, go below. This thing. So in page number around 81, you can get all the things for the doubly reinforcement section. So this is for doubly reinforced. FCK if you have 20, so you have to check this chart, and FI is 250, then you have to check this chart. You can get this value from the left corner, but we in our case what we have the 25 and 415. Okay, so just remember these things. Now 25 and 415 we have to search. This is for 25 and 250. This is 30. This is also FCK 15 and 415, but we want FCK as 25. So this is 20, and next page is our FY 415 and FCK 225 that we want. You can see in 225 and 415. Okay, so it's clear, I think. So now what we have to do, we have to go, sorry. Okay, we are on the page. Now you can see some type of parameters here. What these are, this is returned mu upon bd square. I written it as here mu upon from it bd square. Okay, this is in Newton per mm square. You should have the dimensions also, and these are the d dash by d ratios. This is 0.05. Then you have to check this table, d dash by d. If it is not clear, then that's why I should write it here. These are the content. D dash by d is equal to 0.2. Okay, and that these are PT, means percentage of tensile reinforcement, and these PC, percentage of compression reinforcement. Same PT, PC. Okay, so this is the same for all the things. So now you have to what calculate? You have to calculate mu upon bd square and d dash by d ratio. That's it. So I calculate what? Mu by bd square. So calculate mu upon bd square. Put the value 462.5, but we should in what? Newton per mm square. We have seen the dimension of, we have seen the unit also on the SP16. So Newton, for Newton you have to convert it by 10 to power 3, and meter also is there, you have to take in an mm. So again multiply by 10 to power 3. Now go BO. B is what? 300 mm, I think. 350 and 350. Okay. 350 mm. What is the effective depth? So you can get effective depth. Where? This is not that here. Here. It will come out as 460 mm. For which condition? For which condition? If I take the bar dia as 20 mm. So you should know what we have to take the dia of the bar. So I take it as phi is equal to 20 mm. Then it will come out as 460 mm as effective depth. So these type of calculation you have to done first before the chart. So now we go there. So D is what? 460. Okay. Remember this thing. What is your D? B is 350. This is our 460 and 460 because it's in square. So I come out in calculator again. Now what? Multiply by what? 10 to power 6. 1, 2, 3, 4, 5, 6. These are 6. Okay. Divided by 350. Enter. Divided by 460. Enter. Divided by 460. Enter. That will come out as 6.25 approximate value, but not in lower side. You have to just take it in higher side because it's the moment applied. So you can't underestimate the value of the external things, means applied things. So that is 6.25. And second factor is what? D dash by D. So what is the D dash? You have get this thing. What is the D dash? D dash is our 40 and D is 460. Okay. 40 and 460. 40 and 460. What is the factor? that is as 0.087. This is the factor. Okay, so now you have the both the things. Just you have to go to the chart. 0.087 I write it there. So d by d dash, it's our 0. No, this one not 0.087, and MA by BD square is what, 6.25, I think 6.25. Yeah, this is 6.25. So just you have to check the chart. So I go down. So 6.25 you can get at here, this one. Between of these I write it, this is 6.2, this is 6.3. It may be blur, so you have to just download the SP16 from the browser and you can see all the values clearly, 6.2 and 6.3. So in between of that you have to take the value. So I take it as 6.3 because we can design the higher side, that will be the more moment of resistance. So I take it as 6.3, and if you want to calculate the exact value, you have to just interpolate between the 6.2 and 6.3. That will become as 6.25. Okay, now the second value is what, d by d dash. D by d dash is what, 0.087. Where it should be lie, in between of 0.05 and 0.1, in between of 0.05 and 0.1. So I take the value of what, first of all you have to take the value of PT. So PT is what for 6.3, 2.016. I write it 2.026, not 16, this is 26, and PC is what, 0.871. Okay, now again for the point 1, value, that is 0.2.072 and 0.928. So you have to just interpolate this value and this value. For the 0.05 and 0.1 you have to get the value for 0.087, and if you want to take some higher side, so you can take by the approx, by the common sense only. You have to just use your common sense. So what should be the value, if it is 2.026 and 2.072, so you have to take just like 0.6, 2.06, it's okay for the value, and this for that 0.928 and 0.871. So you can interpolate and you can get, but I take the approx values. So 0.991, we can get some higher value, no problem. So 2.06, what is the value is PT, this is the value of PT. So I write it 2.06. So I get the value of 2.06 of the PT, and PC I get as 0.91. Okay, so these are the PT value and PC value. So how you know what is the PT? So I give the idea what is the PT at here. So PT is our AST by BD multiply by 100, that is our PT. PT means percentage tensile reinforcement, PC means percentage compression reinforcement. Okay, so percentage for what, percentage for the all effective cross section area. That's why we have to divided by effective cross section area, that is what, B into D, and for the percentage you have to multiply by 100, and for AST, and this is what, PC is what, ASC for the compression effective area, and multiply by 100, that is your 0.91. So you can get AST from here. So AST is what, 2.06 multiply by B is our what, 350, D our is what, 460, and divided by the 100. So you can get the AST from here, and ASC from here, so you also can get 91 and 0.350, 460 by 100. So just open the calculator and I go for the calculation. Multiply by 350, multiply by 460, divided by 100, it's give 3316. So 3316 means you can take it as 50, some higher side, 3350. Now second value ASC, this is what, So I have to just divide by 2.26 and multiply by 0.91. 1460. So 1470 I take. So these are the values of what AST and ASC. But we have to check. But we should get the value for what? How many number of bars we have to establish at bottom and establish at top to get this area of steel at both the sides. So die of bar we have taken already 20 mm. So you can get the number of die of bars. What? Divide the total area. This is for tension. Okay, tension. So total area is 3350, and the area of one bar is equal to pi by 4 multiplied by diameter ka square. So by this way you can get NT and NC also. Means number of bars in compression. Pi by 4 multiplied by 20 square. It's come out as 314, approximate 314 mm square, because it's a very ideal data. So you can just memorize this also, because if you solve pi by 4 into 20 power square, then it will come out as 314 mm square. It's the area, cross section area of 20 mm dia bar. So you can get the number of bars here, 3350 multiplied divided by 314. Okay, that's come out as 10 bars. So not tens, 11 bars, because that will come out as something value like that. And second is what? 1470 divided by 314. That is 5 bars approx. So these are the number of bars that you have to establish in your cross section. 1 second. So I draw this again. So this is the cross section of your beam, and this is your compression side above the neutral axis. This is neutral axis. So in the compression you have to establish how many bars? 5 bars. So there are 5 bars. Okay, 1 2 3 4 5, and at the bottom 11 bars should be there. So how you will manage 11 bars in T 350 mm width? These are 1 2 3 4 5 6 like that, and 5 you have to take here like this thing. But is this correct arrangement of the bars or not? So how you should know, how you will get this is correct or not? So there is some specifications in IS code 456 that the I draw, because in drawing it will be more easier to understand. If it is 20 mm dia bar and it is another 20 mm dia bar, so the distance between these two should be 25 mm approx. Okay, approx 25 mm. And from where you can get this type of value? So there is a section in IS 456, you can get horizontal spacing between bars. What is that? That is phi max and maximum size of aggregate plus 5 mm. So you have to take the maximum of these three values. So phi is what, our 20 mm, phi max is also our 20 mm, and the maximum aggregate size is generally taken as 20 mm, and that will become as 20 plus 5 25. So what is the higher value is 25, maximum value is what, 25. So what is the spacing? That is generally come out as 25. If the die of the bar is less than 25, you have to just memorize this thing. If the die of the bar is less than 25, then you can say the spacing should be minimum of 25. If the die of bar like 30 mm, 32 mm, 30 mm is not exist, 32 mm. So phi will become 32, it will become phi max 32, and it will already become what, 25. So you can't say that the spacing should be more than 25, because the 5 max will become the maximum value from these values, so that will become as 32. So you have to maintain the 32 spacing in between that. Okay, so now we have to maintain the 25 spacing. So how many bars you can put at here in single row? In single row, how many bars you can put? So you have to calculate these things. Okay, like I cut this section, below section, I cut the lower section, and no, I don't want the arrow. Why it will come out as arrow? Okay, and this is your center line. So I draw this figure. Okay, this part only. What is the width? 350 mm. Because we get all the things, 11 bars of this, 5 bars of this, just we have to arrange them, that how we will arrange these things. So this is our 350 mm width, and we have the how many bars, how many die of the bars? 20 mm, 20 mm, and we have to spacing maintain as 25. So how many bars you can put? So if you put 2 bars, then how many distance you need? Because you have to maintain the cover also, like these are my outermost bars. Okay, these are my outermost. So you have to maintain the nominal cover at here also, at lower and at this side. In both the side you have to maintain the nominal cover. Here also, what is nominal cover? Nominal cover we have to take 30 mm, you know, in the starting. Then when I am doing the calculation of d and d dash, then we get the value of what? Nominal cover as 30 mm. So it is 30 mm, it is 30 mm, and it's already was what? 20 mm dia. So they take the dimension how much? 30, 20, 20, 30. That will be 30, 50, 50, 100. So 2 bars taken the 100 mm spacing, 100 mm spacing from this area. Now what you should do? Now think about it. What you do? What to do? Tell me. Because I am going thoroughly from the beams design only, because the beam design is so complicated due to this type of things, because you can get these values easily. This is the everyone can get this thing, but you can't get how and in which way you have to arrange the bars, because that they will create a problem. Okay, so how many spacing it can it occupy? 100 mm. Now we have remaining spacing as 250 mm, and if I put 1 bar, so I have the maintain the distance as what? This is 25 mm again, and that will occupy as 20 mm again, and here I put a bar also, so this is 20 and this is also again 25. So what is the value it is occupied? Again 25, 25, 20, 20. So plus in this 25, 25 2 times means 50, and 20, 20 2 times is 40. So it will become as 190 mm, and we have just put the 4 bars. Okay, we have just put the 4 bars. If now how many distance we are remaining? 350, and it will become as 160 mm, because if I put 1 bar I put, then how much distance I left? How much distance it occupy? 25 plus 20, 45 mm. How much we have? 160. So how many sets we can get? Just divide 160 by 45. How much? 45 2 times of 90, 90 as 135. Okay, so 3 bars we can put easily. 1 bar at here, 1 bar at here, and 1 bar at center. Then how will it become? It's 25. It's already 20. This is 25. This is 20. Now this is 20. So from here to here, how much distance? 30, 20, 25, 20, 25, 20. Okay, so I calculate this one. 20, 25, 20, 25, 20, 30. How much it? 20, 20, 20, it becomes 60. 25, 25, and then 75, and then 80. Okay, and it is 140 mm. 140 mm from the right side and 140 mm from the left side. that is 280 mm. Okay, total is 280. How much left? 70 mm. In 70 mm, 20 mm it will occupy. Remaining 50 mm, that will be 25 at here, 25 at here. Okay, so in this way you can put only how much bar? 1, 2, 3, 4, 5, 6, 7. 7 bars only. But we have to put how many bars? 11 bars. So 4 bars we have to maintain where? Now where you have to put? In the upper layer. In the upper layer you have to put the bars. Okay, in the upper layer you have to put the bars. So 4 bars you can easily put first and the centroid, or you have to just put very small dial like 8 mm, because we have to make the symmetricity also in the cross section. There is not unbalanced structure, unbalanced reinforcement detailing should be there. This is I put at 8 mm and these are of 20 mm because we can't put 4 bars in symmetric way. There should be 1 bars at the center. This is 20 mm and this is again 20 mm. Okay, so now we got the cross section detailing, reinforcement detailing in the cross section of tension zone. So this is tension zone. In compression you can get easily because I have given the all of idea. You have to put 1 bar at the centroid because we have to put how many bars? 5 bars. So 1 bar at the centroid and maintain from the half of the portion 2 bars put in symmetric way. So it is easy. That's not so much difficult that we should do. So it is easy. Now what is the effect? You have given this type of arrangement in the tension zone. What is the effect? You know what is the effect? Because I take the D dash as what? Clear cover plus what? 30 mm. Sorry, clear cover plus 5 by 2. That is what? 30 plus 20 by 2. That is our 40 mm. Now, what is your D dash? Now, what is your D dash? Your D dash will shift from this CG to this. Some upper side. Something. That will be something. Because there are 5 bars and there are 7 bars, so the efficient will be more at lower side. In between of these, the effective means the CG of this set of the bars will be downward between these side. Okay, so it will be shifted downward, but overall it shift upward because there are 2 rows of the bars. There are 2 rows of the bars detailing, tension reinforcement detailing. That's why your D dash will increase because the D dash is what? Effective depth. So effective depth will increase with 30 with 40 mm. So D dash will become more than 40 mm. That may go up to what? That may go up to what? You can get it as 4. You don't have to calculate this thing. What is the D dash? I just giving you the idea. D dash will become like 50 mm. If your D dash will become 50 mm, then your D will become what? 50 by, sorry, we have the overall depth as 500 and D dash is 50, so it will become as 450 mm. Now you have to take the this ratio also, 50 by 450, that will become as what? 1 by 9. Okay, previous we have taken the value of D dash by D. What is the value? What was the value at that time? D dash by D value is 0.087. What was the value? 0.087. Now it will increase by what? 0.1. Okay, 0.111 like that. Now it will increase by width 0.111 like this. Okay, it will increase, you know. Now what is the problem? If your D dash by D ratio will increase, then you have to go to the chart and you will see that D dash by D ratio for 0.11 will become higher than 0.1, and you have to take the value of both PT and PC from 0.087. That is wrong. Means you have underestimated the reinforcement. means you have the underestimate the reinforcement. Did you get my point what I'm saying? Because previous case you have the d dash by d ratio is 0.0827, but now you have the ratio is become 0.111, means higher than with 0.1. If your ratio will become more, d dash by d ratio will become more, so what is the effect? You can see, if your ratio is 0.05, that time the ratio pt will 2.026, and it will increase to 0.1, then the pt will increase. You can see, pt will increase. And if I take the 0.11, what you get? 2.123. 2.123 for 0.15, but we want for 0.11. That will be intermediate from where? Like 2.072 and 2.123. So you can take it as 2.1. That are more higher. PT is what? 2.1. PT is what? 2.1. And the MU by BD square ratio will also affected due to this. You can get the MU by BD square ratio again, because the depth will also, effective depth will change. Before that we have the 460, now we have what? Now we have what? 450. Now we have what? 450. So you have to just 462.5 10 to the power 6, that is same 350, 450 square. So I get this value. Once again. I am just give you idea. Just don't nervous by these things, because it's some complicated due to this type of calculation. This is for your practice. That's why I am giving this type of thing to you. 6.52. It will become 6.52. But at that time, that is what? That is what? 6.25. 6.52. Now go to the table. What is the effect of it? 6.52 as the also the higher value from above. Means due to this type of arrangement, you get wrong results. That's why you should take what? Phi should be high. Die of the bars, you should take it as like 32 mm, 36 mm, 25 mm. This type of bar dia you should take. If you take this type of dia bars, then I think you didn't get this type of problem. Means the number of bars will reduce. There is one thing also, because the 25, if you take 25, then the horizontal spacing is 25, remain is 25. Then you take 32, then it will become 32. If you take 36, then it will become 36. But the number of spacing will decrease parabolically. हाइपरबोलिकल शेप में ये क्या करेगा? डिक्रीज करेगा. इट विल डिक्रीज इन हाइपरबोलिकल शेप. नंबर ऑफ डायर बार्स बाय द इंक्रीज इन डाय ऑफ द बार्स. Okay, so this is the all the theory about beam design. But it's not done all the things, because I have missed something also there. What are that? What are those things? Those are shear design. I didn't do the shear design. Okay, so that we will see in our next lecture. So to just take these values. What are the values of PT and PC? So what you should do? Now you should do the what? You can increase the size of dia like 32 mm. If you will increase 32 mm, then your D will reduce. What? Your D will reduce, because the phi is 32, so D dash will increase and D is reduced. So D will reduce, so your MU by BD square will increase, and D dash by D is also increased. That's why your PT will increase, PC will increase, PT PC will increase, and then your AST will increase, ASC will increase also. Both the reinforcement area will increase. That's why we have to always take the higher values for all the things. Like I have taken the PT percent as higher at in the table, and PC percent is also I have taken the higher value. That's why we should take the higher values so that we will not face any problem like this. Okay, so you have to just I have just given the idea to you that because the length of the beam is so large. I see you again. One second. This type of beam you didn't see, I think. 10-meter beam who have the section 350 and 500 mm, and the loading is like this. 10-meter long beam. You didn't see this type of beam in your life because it's a so lengthy beam. It's a so lengthy beam, and who have the size very less. Because if your B and D are less, then your mu by bd square will become higher. That's why you should remain. That's why you will get the AST and SC higher, and you will get the is higher. Then you have to take the NT higher and SC higher. So you have to maintain these things also. So it's will come with practice, because these are the practical things. So if you do this type of practice again and again, you will get the very good idea regarding the beam, regarding the size of the beam, die of the reinforcement. So that's why I have taken this type of lecture series, so that you can get all our idea about the beam design only for the flexor, not for the shear. Okay, flexor design I have discussed only. The shear design I didn't discuss. So okay, this shear design we will discuss in next video, because it's also a interesting part. So okay guys, thank you all.